All right, so I'm finally freaking doing this. I have been going to start recording my coding marathons, and I just haven't had the right equipment to do it. But I finally got OBS set up, and I'm going to be just not coding alone. Honestly, it sounds sad. I'm not sad about it, but it is a solo sport, so you spend a lot of time just talking to yourself. I figured I'd record, get a laugh out of it, put it on YouTube or some shit. Um, but all right, so here's what I'm working on. I started with Codecrafter's SQLITE challenge, and at the same time, I was working on something at Microsoft where I needed to use Rust and SQLITE together to create this ingestion pipeline for log data for local development. What ended up happening was that I ran into a lot of nitty-gritty details about SQLite regarding file locking and transactions and updates and all that stuff, and I ended up doing a deep dive. I have always had an interest in storage engines, especially something like SQLite has been on top of my mind literally from the first day I got into programming. It was like programmers use database, but which programmers write databases? And SQLite was the first database I ever interacted with. So anyway, the motivation of this project is pretty much, I'm not completely sure where this is going. I started with the idea that I will just build a SQLite replica, completely in Rust. That's not where this is now. At this point, all I want to do is I want something that's backwards compatible with SQLite file format, so I can use stuff like the SQLite file viewer and whatnot, all the tooling around it. But all that I really need is the B trees to work in a certain way, so that I can extract a particular set of APIs and create a storage engine that just leverages the B tree format. I've already implemented a good amount of it. I think I'm around 2,000, 3,000 lines of code in this repository already. I can quickly show you what I support at the moment. We can just dive into the main function first, right? So let's go to main. All right. It's pretty simple. Right now it's set up as a CLI base tool. You go ahead, you run the binary, and you have a few options, right? You have you can view the tables, you can view a particular table, you can look at an index, and what the vision over here is that all of these CLI function CLI capabilities that I have in here are just a part of a library that I can directly use in Rust and build a database around. But first I need a storage engine, which is just a persistent B tree. And actually that is all that, well, that is not all, but when you look at how SQLite works under the hood, there's something there's the SQL part of it, there's a virtual machine part of it, but all of that just comes together to work with a B tree on disk. And I would be okay if I could just get the B tree part of it down while still being backwards compatible. Anyway, so with that said, I'll quickly show you the kind of feature I'm working on and I'm thinking about implementing. So I have two logical separations, right? There's a read path, there's a write path. For read path, I just want to be able to give you ability to query. It would be a simple API in Rust that I can just call. And then for the write path, you have a create table, delete table, and then a set, or I guess an insert is a better name for this anyway. But we're actually far from the write path right now. We're only sitting at the read path, and all of the code that I have so far just supports the read path. So you guys are pretty caught up. I think you'll see, you know what, let's just go a little bit deeper, right? So the way everything is set up, and you know what, I can probably make, let's go to notes. Notes.md. Alright, so the way SQLite's actually working, or how SQLite B trees databases work, and I'm assuming you have some understanding of B trees, or at least don't forget B trees. Just think of binary search trees, right? Or if you don't know binary search trees, just think of trees. that I expect you to know. So a tree is going to be a data structure, while a binary tree is going to be a data structure where you have a parent node, you have a left node, and you have a right node. What makes it a binary tree is that each parent can only at maximum have two children. So binary. If this was just a tree, there could be a child one, like A is the parent for child one, for child two, and child three. So a binary tree is just like a particular type of, well, it's a type of a tree. A quad tree is just a type of tree as well with 4 children. Now, the next progression to this would be a binary search tree. So let's say instead of like using just the idea of a node, we give these nodes some values, right? So like, let's say that the node A intrinsically has the value of 1. Child has, and you know what? Let's just do this. Yeah. So basically, when you have a binary search tree, the only rule that you have is that any child to the left must be uh, must have a value that is less than of its parent. So if we have a child B over here, it must be less than 1. And anything that goes on the right of A, the right child of A, should be greater than or more than 1. Right? So let's just do this. Fun fact. I actually don't know which side you call greater than, less than. I just remember the crocodile rule because back when I was in school, at some point my parents moved me from a really bad school to a good school when we moved to Mumbai in India. And the first day there was a test, and that was the less than equal to it. I just completely flunked it. But the teacher told me the crocodile eats the bigger one, so whichever side that goes. But the whole concept of the A has to be less than, well, anything in B has to be less than A. Anything in C has to be, it could be 1, it could be 2, it could be whatever. Now you come down to, now each node can further have nodes. So the data structure is like recursive in nature, right? What that means is whatever applies to the parent can also apply to the child, and its child, and its child, and it just keeps going as long as the data structure is there. So D would have to be like -5 over here, and E would be more than -1 but less than 1. So realistically only 0. Like this, you can like just keep on building this tree out. So that's a binary search tree. Now, why would you use a binary search tree versus having a list of just sorted lists or something? Well, let's not think about sorted lists because that makes this unintuitive in nature. But the whole point of this over a simple binary tree, right, of using a BST over a binary tree would be that because we know the parent and we know that the left child is always less than the parent. Let's say if you want me to search for the value -5, or well, let's not do -5. Let's do 0, right? Instead of going traversing all of the nodes, right? So all of the tree's nodes, like one by one, and finding 0, which would take a linear time complexity in the worst case scenario, right? So let's say instead of searching for 0, what I was searching for was, let's do this. So C has, I hate this part about working with, like, trying to like show someone a tree in a code editor because it's really hard to draw it out correctly. But let's see this, right? So let's say F is the left child of C, and that has the value, or let's not even give F. Okay, let's do this. Let's give 5, A, B, C, D, E, F. Let's give this 3, E, F, G is 100, right? Let's say the query that we got, well, like find me the node where the value is 100. I would have like in a full traversal mode where I'm not using the capabilities of a BST. Let's just say it was a binary tree. I would end up looking at all of the nodes starting at A, going to B, D. So I go depending on how I choose to traverse a tree, because there's multiple ways to traverse it. But the concept is that I would end up looking at all the nodes, and the last node I would reach, again, let's just say I went in a manner where this is the last node that I look at, I would have a time complexity of O of n, right? But when you have a BST where you know the constraint where each left child is lesser than the parent is satisfied, what I will end up doing is, all right, 100 is 100 less than 1? Yes. I move here to the right child. Now the right child is 100 more than 5. Yes. So I keep going further, right? And without going into explaining how we get to time complex, like how we derive time, like O of n, or not O of n, sorry, the big O complexity, this actually comes out to be log of n, right? Geez, I clicked. I sometimes like type out, like I click, what's it called, the caps lock key, and then suddenly all my Vim key bindings like lose their shit. So that's exactly what happened right now. But anyway, so you would get O of log of n if you use the constraint of left is less than parent and right is more than parent. Now that's what a BST. Well, that's how a BST is working. Similarly, another. Now, why can't we just use a BST for everything? Sounds great. Like you can get O log of n. You can search through shit really fast. Okay, cool. But did you notice how I actually tailored the values in this data structure to make it O log n queryable? If when we were building this tree, we were in a situation where A of 1, right, result, and then the next one that we, because as you're building it, you get A of -1, and then you get C of -5, then you get a D of -6. Now, even though this satisfies the BST, it's actually a linked list. A links to B, B links to C, C links to D, right? And that's just what it is. So no matter how we do like a search on this, if we have to go for the worst case scenario of big O complexity, we will end up doing a linear lookup, which is O of n. And that is when you scale the algorithm, it's not as performant as O log of n. Now, what we're looking for is something that balances itself, right? The balancing is basically when what you're looking for is you don't have a skewed tree. The tree sort of, on every insertion, it corrects itself just a little bit, such that all of this stuff is on the same level. So, off the top of my head, right? So, let's just take this. What a balanced version of this would look like is, as stuff is coming in, it would adjust its nodes, right? So, actually, let's just go with this, right? A of 1 is the first one. We have B of -1 come in, so this guy goes here, A of 1. When we have B of -5 come in, what we can do is we can move B -1 here, and we can use C -5 here, right? And now when we have D come in, D could go, well, assuming we're sticking to binary trees, D would have to go here. But if this was not a binary tree, D could also go here. What you want is you want a wider tree in our scenario than you want like a skewed tree. Like you don't want a wider tree because there's certain issues over there as well. Basically, you just want the tree to be skewed. So you use what are called self-balancing trees, right? Self-balancing trees for this stuff to work, right? And there's quite a few implementations of self-balancing trees. So you have the red-black, you have, geez, is that all I got? No, we have B trees. It's a self-balancing tree. You also have B plus trees, or B trees, B plus trees. I swear it's like Red black is the one that always comes to my head. But there's more. There's more, and I'm just blanking out. You know what? Give me 1 second. Let me grab my algorithms book. So this one was recommended to me by my mentor, Craig Shirts and Jim Warner, and it's just like I think this is the lingua franca of like learning data structures and algorithms for a long time. But they have a lot of chapters on what do we call balancing trees, right? So let's go look it up. Yep, there we go. So you have red black trees, binary search tree. Which one should we look at? Which one should we look at? Augmented data structures. B trees 497. So let's look that up. Pretty sure I have it like already set up over here. All right. Yep. So we have our chapter on B trees. Jeez. Okay. And the core thing. Well, I'm just going to keep this as a reference book next to me so I can look at it. But the core thing that we're working with in a B tree is that what is this? Okay. So the core thing we're working with in a B tree, right? And like let's just isolate it to this. And honestly, like B tree should just be its own full video because it needs so much context that even I honestly like its read path is so separate. It's so different from its write path because you have to do these things where you have like promotions and you move these nodes with each insertion such that the leaf, all of the leaves, right? All the leaf nodes. So leaf nodes basically the last layer, last child with the last child with no further children. And the topmost node is called the root. The topmost parent is called the root node. But in a B tree, what you have is, first of all, there's no all of the leaves have to be in the same. The constraints are all the leaves have to be in the same exact layer. Each parent can have more than one child. I think that's called the branching factor, and each child further has more children. So that's pretty much it. The thing is that the children of each parent are also sorted least to most, and that's another constraint that you have to have there. And if you're not getting like anytime I think of something sorted, you're searching for something that's sorted, you can make it happen in O log of n. But why are B trees the thing I'm like fixating on? Well, because SQLITE's built on top of B trees. When you have a data structure that only requires you to look at a node and make a decision, versus, let's look at a quick competitor, right? So if I was writing a database, which means get and set, a hash map's a great option if everything just needs to sit in the memory and not on disk, right? So you have a big dictionary of like 1 million, 2 million, 3 million objects. I don't know, like depending on how big the data in that is as well. And you can just have O of 1, like constant time lookup, right? It's just going to hash it, go to the pointer and on your RAM, give you the value from there. Get/set, right? GDE/set. Okay, fuck it, I'm gonna fix it. Let's fix it. Get or set. But what happens when the data that you're working with needs to be persistent? So let's say your program crashes and you want to reboot and you don't want your data to be lost, or let's just say the data is so big that your process keeps on hitting a out of memory issue, right? Because you can't hold everything in RAM. There's a reason why you have secondary storage on your device. But secondary storage is also slower. So it's this memory hierarchy thing, right? Where registers are super fast. You have caches after that. Then you have the RAM, and these are all the order of magnitude gets more and more like how each is slower than the other. But then you have the disk, and suddenly disk is just so much more slower than RAM that it's that you really need to be smart about how you store and work with data over there, right? So the thing is with B tree, what you can do is you can store each node on disk, somewhere on disk. I won't even tell you where yet, but you can store it somewhere on disk, and from that point, right? So from each, you only load that node into the memory of your running process, and your program looks at that node, deserializes it, right, from the byte format on disk to uh, whatever you want to serialize it into. Like in our case, a node of a B tree, and then it proceeds to make a decision whether to load which node to load next. Um, and it goes on making this, so now you can store a lot more data, right, in your database than you would in your hash map without crashing your process's memory. The other thing is that because this is data on disk, I close my process and I restart my process, the data that was written to disk is persisted. Uh, and that is the point of using B trees. Now, how SQLITE databases work is that each table is a B tree, and a table is just a B tree, right? An index is also let's not go into indices yet. We'll just talk about a table because indices are not very different. They're just a layer of interaction, and I find this like particularly beautiful because I forget who said this, but someone spoke about how any problem in computer science can just be solved by indirection, and that's actually very relevant to how indices are working. But sorry, I go off topic over here. So let's go 36 lines down. You have a B tree. Each database, right? Each SQLite database is just one single file that is being logically divided into chunks called pages. Now, for anyone who's new to systems programming, such as me, I'm not that experienced. I'm still 24. I'm pretty young. I'm learning this shit. Do not confuse this with like memory pages from like mmap system call or something, because that's the first thing. I was reading this book on systems programming and I just learned like mmap and stuff. And I was like, okay, cool. I know what a memory page is. And I was looking also at the same time, trying to get into a database and understand that stuff. And there's like talk about like that it spoke about pages, and like every like data storage engine is using these concepts of pages low key. But I conflicted them, so it's an overloaded term. But what we mean by pages is just a logical chunking of segments of the big database file, right? So you have a file in your file system, nothing different than a text file, nothing different than like a like a video file, anything. It's just a byte. Like, don't think of like the format. So like a text file would be like a encoded, like the bytes have a meaning and you know what that encoding is. So it's a text file. Similarly, like a SQLite file has its own encoding, its own byte-based encoding. It's not a text file; it's a byte-based like file. Yeah, it's got these chunks, segments, and these segments are usually the size like 512 to something to the power like 2. Like I SQLite file format sizes. So let's just go here, right? So SQLite file page size. Yeah. So yeah, it's between 512 and 65536. Okay, cool. 512, 65536. And on my system right now, I'm working with 4096, so 4 bytes. That's 4 KB chunks of my file. The way a database is written is, well, a SQLite database is written is that the very first few bytes, like the first 100 bytes, are holding database metadata, right? Well, this is just stuff like, let's just look at what the database metadata looks like. So the first, wonderful. I'm so glad I have this here. So the first 100 bytes will store stuff like, what is the page size, right? 32768. Okay, cool. Yep. What is the file format version? Blah, blah, blah. We can skip this. Size of database file in pages, page numbers, basically just information about how do I use this, like about the database itself. So while I've been exploring this and any other file format realistically, like it's a very common pattern to have metadata for that data, and then further stuff in that data. And it just makes sense because that's how you can do parsing with these things. But there's another thing that we get to after we have the database metadata, right? Which is, okay, now you know about the database, but what about the tables in my database? Well, the way that is working is that right after the first 100 bytes, we have the schema table. So the schema table, so think about this, right? You have, uh, let's just think of like, well, to us, a file is nothing but like a sequential, or the way the file system exposes the files and the APIs expose reading and writing files, like this sequence of bytes, right? So think of this, right? Uh, the first 0 to 100 bytes are metadata, followed by n bytes of the schema table, followed by bytes of something else. Like it's all just like you can just keep reading these byte and keep going. Um, but the schema table is actually a special byte format, right? Schema table. And we can go into how you read a schema table and what that looks like. Uh, but what it holds is basically uh, it's holding these rows. It's got a table that is byte represented on disk, and it's holding these rows that each row holds a database object. So that could be a table or an index or a trigger, and there's maybe one more. But we'll just stick to table and index, right? And tables and indices are just B trees, and so are the other objects that are being held by a schema table. And you know what? We can even look at table info. Yes, wonderful. Um, this is the info that it holds. It holds the object type, so this could be table or index or blah blah blah, the name, the table name that this is for, and then the root page number. So that's important. And a SQL string, and SQL strings is what I'm trying to work on today. The SQL string is basically the create statement that was used to create this table. And we'll get to that in a second. But the core thing is the root page number. So root strikes a thing in my head. I'm like, root page. Okay, each page is basically a node for a B tree. And the root page is the page that holds the root node for the table's B tree. And that's actually about it. Once you have that, you have the first node, and from there you can load the root node, and based on the query, you can traverse this B tree and get to it, right? So schema table holds root nodes for each table's B tree, and each table gets its own special B tree where it stores its data, right? And then really quickly we'll go into indices. What is the index B tree looking like, right? So schema table also holds the root nodes for each index B tree. And all that an index does is, given what you're indexing on, it stores, well, real quick though, remember how like there's a value that we're working with? Well, that's the key. That's the key for each row. And what if I open up the sample DB? Maybe I can show you that real quick. So you see how there's like a intrinsic key that each row has? Just remember this guy, okay? And what's happening with the index B tree is that the index holds, like you're gonna say, hey, like, okay, in sample DB, let's say I create an index on name, or fuck it, let's create an index on age, right? What that will do is it will create a B tree where the key is the age, right? And the value for that key will be the row. So it's a separate B tree. Imagine this whole thing's its own B tree, and that's its own B tree. So now you can, in O log of n, you can traverse to find the things that satisfy the age constraint in a query. Say, oh, this is the ID. Then you go to the table B tree, and then you use that ID, or the key. Just gotta stop using ID. ID is separate. Key is separate, right? You use that key to do a really quick look up on the B tree, and now you don't have to do like full table scans for anything, right? Indirection. This is its own B tree for indirection that is used. Index B tree for index that is used to isolate one or more properties of the table B tree to look up stuff faster. Yeah, it's a layer of indirection that we're adding so we can just do a lookup faster. Anyway, that's probably not the best explanation. I'm not the best programmer either. I'm just doing this so I can code and talk, and I love talking. I'm a yapper. She can't tell, and I've always wanted to like code, give a presentation, and do demos, and this is me living that dream. Hot girl summer, hot girl summer. That's what this is. Anyway, I hope no one reads that out loud or says it out loud. But okay, cool. So with all that said, you know how a database is low, like the storage level of SQLite is working. Um, Now, what I'm working on today, let's go to main, let's close this, let's look at get. So I'm supporting this like whole get command on my CLI, where you can give it a table name, column values, like what columns you want to select from that table. You can add some filters, right? And right now I'm only supporting things like less than, greater than, equality, and not equal, equal and not equal, right? Delimited. Okay, that's okay. I actually don't need this comment anymore, so I'm just going to get rid of this. I also do not need this comment anymore, and I'll tell you why I don't need it. Actually, you know what? Let's keep this. Let's keep this. Let's keep this. This is going to be. Let's put this. And I will just move this guy. Okay, cool. So what I'm working on is that you can sort of like, without writing complete SQL queries, you can give this like a very strict query to the CLI, and the CLI uses the B trees and all indices and whatnot to do a really quick lookup. The trick over here is I need to do some validation. Like, let's just say you have a table, you don't know what the columns are, and you just say, hey, make me this table. Well, that's not going to work out very well. You can't work with something that's not a real column. And the values you use for, well, you have an operator, right? You have a left-hand side, right-hand side. The right-hand side, like, if you have a, let's say like a string on the left side, like a string type, you can't be comparing it to like a F32 or like a number or null. I don't do null actually, because you could say null where this is not null because column may be optional. But anyway, I digress. But yeah, there's some validation we need to do. Now, the tricky part is, remember in our database B-tree info, right? The way you find the schema is actually stored in the create statement. I don't know how to parse that really, like, and I want to make something that's just, you know, like that's legit. Like, I don't just want to write code for like the heck of it. I want to write something that I'd be proud of. So let me just open this over here, SQL parser. Yeah. So I need a very specific parser that can give me all the details from a create statement. Now the create statement is a string, and I need to go from a string to something super, like something structured, right? And the first thing I thought of is, okay, we have a DSL, and we wanted to go from a DSL to a data structure. That sounds like something that compilers would be doing, right? Like, and that is what it is. You have a, well, not in our case, not a stream, but you have a string of characters. You need to go from characters to tokens, right? Tokens to what's called the abstract syntax tree. It's a lot of words. It's a lot of words. It's basically just saying, well, these tokens have some sort of structure to them, right? Like a select is like if you think of it as an operator, well, it's going to have a, what are you selecting? What are you selecting? Like, what are you selecting? What are you selecting from? It's a left-hand side, right-hand side, and like other like sub-children, like it's a nest, it's a tree. Like, again, we have a freaking tree, but this is an in-memory tree that we need to write. But we have an abstract syntax tree. And then from that, we can go into the data structure that we need, which gives us all the information, which is, in our case, what I do, which in our case is like, I just want a vector of string, so a vector of like tuples of string and serial type. And I don't think that's the best way. I'm just gonna make this slightly not clean, just column, or let's see, table schema, right? Or let's not even do table schema. Let's say each column, right, has a name and a data type. And if I just want schema, what I can do is I can just get a vector of columns. 8, so let's equal column. So SQL column. Alright, cool. Alright, now this is where the part gets really tricky, and now you're going to see me start struggling a lot more. I know how to write a tokenizer, and to go from a tokenizer to abstract syntax here requires you to understand how to parse. 1 second. Let me just like this. Yep. So go from like an abstract syntax tree to going into a data structure. I need to use, well, a lexer and a parser. Right? A lexer and a parser. And those are two separate components I'm going to have to write out. So I moved all the code for that part into its own SQL parser. The only thing we need to parse is this guy, parser, which requires us to know the grammar. So grammar is basically the rules. Lexer gives us tokens, which feeds into the parser, right? Parser gives us an AST. Okay, cool. We have a lot of stuff that's written over here. So character string or just string feeds into the lexer. Lexer gives us tokens. Parser, grammar, right? Now grammar. The only kind of grammar that like we can work with over here is, well, not the only kind. The one I need is what's called the Bacchus Norm. What's the F for? B and F grammar. I think it's Bacchus Norm form. Notation used to describe syntax of programming language or the formal languages. And I believe the only thing, right, is that it's a context-free grammar, which means I can look at, well, how do you learn what a context-free grammar is? You know what? Let's look up that. And I have another book for that. It's called the Dragon Book Compilers. Super duper famous. I've read a few chapters of this already, so I have good understanding. And we're just gonna go to the chapter on writing a grammar. Okay, where's the one that talks about what a grammar is? Context-free grammars, verifying the language. Context-free grammar versus regular expressions. Ambiguity, parse tree derivatives. Syntax, representative grammars. Some of the grammars, well, role of the parser. Alright, so grammars for expressions suffice, top 3, general types of parsers, universal, top down. We're going to do a top down parser, like 99% sure. Left recursive. I'm just going to go to summary of the 4th chapter, which talks about context-free grammars. Parse tree derivations, notational conventions, formal definition of context-free grammar. Terminals and non-terminals are starting introductions. Okay, let's start writing some of this. We're just making notes right now. Like I cannot code something I don't understand, and I don't need like XML diagrams or anything. I need to freaking understand what context-free grammars are better before I start coding that stuff down, right? So let's just make it CFG, right? Composed of terminals, non-terminals, and productions. I've done this stuff before, so these words make sense to me. They might not right now to you, but we're gonna demystify them as we go, right? So with that said, okay, caps lock again. But terminals are basic symbols from which strings are formed. Token name is a synonym for terminal, and frequently we will use the word token, blah, blah, blah. Terminals are the first components of the tokens output by the lexical analyzer, right? Terminals are basic symbols from which strings are formed, are basic symbols from which strings are formed. Okay. Um, it's just like the building blocks, right? The building blocks, the most atomic unit of your language. In our case, the language will be the SQLite SQL language. There's a slight difference. I believe there's some rules, some things that SQLite is like the SQLite SQL does not understand, like it's omitted. So it's a subset of SQL or like actual SQL. Uh, so anyway, terminals would be stuff like select, create, these like atomic units that are just like reserved for the language, right? Or like, um, yeah, I guess that's about it I can think of. Non-terminals are syntactic variables that denote sets of strings. Um, okay, so we have non-terminals. Non-terminals are, you know what, let's put this in list because right now we see everything is like line delimited, but in Markdown that's not going to be the case. So non-terminals are syntactic variables that denote sets of strings, right? Uh, Non-terminals impose a hierarchical structure as key to syntax. Okay. Um, in grammar, one non-terminal is distinguished as a start symbol instead of strings. It denotes the language generated by grammar. Productions for start symbol is first. A non-terminal called the, and then what's a production? Each production, it's a grammar rule that specifies the manner in which terminals and non-terminals are combined to form strings. Okay, so each production is a rule. Syntactic variables that denote set of strings. Ooh, that's a heavy one, and I'm not able to understand it completely if I'm being honest. Let's see terminal versus non-terminal. Let's ask for some terminal versus non-terminal symbols. Okay. Lexical elements used in specifying production rules. Okay. Elementary symbols of language is part of formal grammar. Non-terminal. Okay, you know what? Stack Overflow. I can always trust Stack Overflow with this kind of stuff. And yes, I know I could be using ChatGPT, but I'm actually actively trying to reduce my usage right now. There's a joy in learning this way, you know, and that joy is called using your own head. Sometimes people just like, I genuinely believe like people will trust anything ChatGPT spits out. This is probably actually a good use of ChatGPT. I'm not trying to like be an AI doomer, but when you're learning something, the experience of digging deep and like going to different sources, picking up a book, all these things are what like make these concepts concrete in your head, at least in my experience. Um, so with that said, yeah, that's why I'm like using ChatGPT for this stuff. Because yeah, probably I could get all like most of these answers just like straight in one go. But no, I want to understand these things at a deeper level. Like I don't want to be a grok brain developer out here, Anyway, let's look at the answer. All right, so let's look at this, right? For in the following parse grammar, terminal and non-terminal are not parse specific, but are considered grammar rules of grammar in general. Parsing has a slight different meaning, but the one I prefer is a conversion of linear structures, string of symbols in a broad sense, to a hierarchical structure, derivation tree. So an abstract syntax tree is a hierarchical structure via a formal recipe, the grammar. Okay, so we know grammar is what takes you from a linear stream of tokens to the hierarchical structure, right? All symbols in a string are terminals, in a sense that tree derivation terminates on them. They are leaves in trees. Okay, non-terminals. Ooh, okay, this is nice. Non-terminals are a form of abstraction that is used in grammar rules. They group terminals and non-terminals together. They are nodes in trees. Okay, I see where this is going. So like, in that case, I would think a select is the non-terminal, and then the values would be terminals. Let's see. In the following parse grammar, greeting is hi, hello, howdy. Person is name, surname. Name is John, Jane. Surname is Doe Smith. A sentence is composed by a grouping of, well, Doe or Smith, John or Jane. A sentence is basically a greeting followed by a person. right? So a greeting would be one of these, and a person would be name and surname, so whatever combination you want of these guys. Okay, so greeting, person, name, surname, and sentence are non-terminals because they never actually appear in the linear input sentence, only in grammar rules. Oh, so sorry. Select is a non-terminal, guys. The select is a non-terminal, but a create statement or select statement, the abstraction would be the non would be a non-terminal. Sorry, select would be a terminal. Yes, and then select and the keywords of the language and the primitives of that language would be the terminals. Okay, that works with me. So what differentiates a non-terminal and a production? That's another question that we need to ask, right? So, um, so a terminal would be the primitive tokens. Non-terminals would be abstract concepts created by combining terminals into a hierarchical structure. Nice. And then a production, right? Production would be the, let's see, what does this book say? Production of a grammar specify the manner in which the terminals and non-terminals can be combined to form strings. Each production consists of a non-terminal called the left side, and then a right side consisting of 0 or more terminals and non-terminals. Oh, all right, we're chilling. Production will be the rules that show how a non-terminal is made up by combining terminals and non-terminals and / or other non. Then it doesn't have to be other. I guess that's a little caveat I need to add, right? Because like it could be sort of recursive in nature as well. Like that's a thing, right? Anyway, I think we're at a really good point. So the book also gives at the very start of the chapter on parsing, which is syntax analysis, this little diagram. I'm just going to show this. I don't know if you guys can see. Let me check if I'm showing this correctly. So let's go to workout routine. Yep, okay. Anyway, so I'm just gonna. There you go. Show that. Yep. So anyway, what it's showing is how a lexical analyzer and a parser are working together, right? So the way it's working is we have the lexer, which takes the input string, and the parser receives a token from it. It gets a token, and like it has the lexer gives you two methods on it. So think of it as a stateful thing, right? You can get a token, and you can get the next token without consuming it. So you consume, you get the next. Those are the two things we're working with. Then the parser at the end of like this entire thing will finally just give you a parse tree. So when I think of it, right, when I think of writing this code, let's go in here. I'm just gonna give it like a very base thing. So it sounds like the lexer. Actually, I don't need to make none of the stuff in this code except this one method needs to be public. So I'm just gonna leave this as this, right? So we have the lexer, right, which is holding an input string and a position on a string. Implement lexer, right? So it has the next token, and then it should have one more thing, right, which would be the peak. How is peak different from like next token? It's not. It's not. We're not messing with that. You have next token, and we should have a consume. Consume. Yeah. Okay. And you know, as you call the next, well, as you call the, so this would be a mutable one. Next token will be immutable. Yeah. You know, this way you can peek the next token and you only change the state of your lexer when you call zoom on it. So this should be mutable, this should be immutable. Okay, so that's a lexer. Now the parser, right, can just be something that takes the, okay, that's actually solid. I'm not going to trust any of this GPT code. Not, yeah, we can honestly we don't even need that. So to do, you know what? Let's just let's do Lexer, and that's going to be mutable Lexer. All right, cool. So the parser is just a function. Like, it uses the lexer, but it doesn't really maintain a state. The lexer, on the other hand, maintains a state, which is why I've got this whole struct with implementation, blah blah blah. But the parser will just be its own thing. And then over here, right, we will construct lexer, construct all parser with lexer, interpret the AST to get schema, and these are all things we need to do. Okay, cool. Now, for the lexer to work, right, we need to understand what are the tokens, right? So what are the tokens the lexer needs to be able to create? And then the parser needs what is the B and F grammar for the create table statement. Okay, yeah, the parser is super specific to create table statement right now. And that is something that I'm okay with because we're only parsing the create table statement. Like, SQL is a big language. And that's honestly, like, I don't care if it takes years at this point to keep coding this stuff out. I'm okay with the fact that when I started programming, projects would take me days. And the complexity, I got better at it on the same stuff, and now the projects took me weeks, like days, like less than days, hours. But then as you step out of your comfort zone, right, and you go to things like you want to write your own language, you want to write your own database, you're talking about years, dude. Like, how guys who write their own operating system, they work on it for years and years and years, and that's just what the progression is. And the dopamine hit from programming is maybe not as instant anymore because you don't see it in front of you. But I also think it's important as I grow as a programmer to work on more challenging things, and naturally that means taking forever to put out anything of value. And if I'm being honest, there's no real value I'm going to deliver with this code. The value that I deliver is just intrinsic to how I feel and what I learn. And maybe this will be the stepping stone to something bigger that I come with. But I need to do this exercise so I can learn. And then when the opportunity comes, I'm ready to show what I'm building. But anyway, without going too much into it, let's start with the lexer, right? The lexer is just taking characters and converting it to tokens. And I think I will put a pause on it once I get the lexer working today. So let's go look at some grammar and shit like that. So I found these two articles. One's a GitHub link, one's like a SQLITE language documentation. But I don't know how legit the GitHub link is, so I'm actually just gonna maybe skip this for now. We'll just go straight to the language one. It's terminal, query language, duplicate. Okay, awesome. So let's dive into it. SQLITE understands most of the standard SQL language, but does omit features while at the same time adding a few features of its own. Documents, blah blah blah. List of SQL keywords is also provided. Nice. So let's get that. SQLITE keywords. Awesome. All right. Create. Blah blah blah. So these are things that the tokenizer would be working with. And while I'm at it, I think I'm gonna because this is something I've been wanting to write for a fat minute, like complete SQL parser, like a SQL compiler that looks at SQL, gives me a hierarchical structure, and then I can do whatever with that SQL hierarchical structure. But we need to get to it at some point. Maybe the lexer, because the lexer is significantly easier than the parser to write. It's longer in code, but it's easier. Yeah, like I've written a lexer before for a few things just for fun, and I think I can pull that stuff off. But the parser, slightly harder, and I'm only going to stick to the create for this project. But I might recycle the code and write a full SQL compiler afterwards. But let's look at this stuff. SQL is a large number of keywords which may not be used as the name of tables, indices, columns, database. The list of keywords is so long that few people can remember them all. For most SQL code, your safest bet is to never use English word as the name of a user-defined object. If you want to use a keyword, you need to quote it. There are 4 ways to quote. A keyword enclosed in square brackets is an identifier. It's not standard SQL. Grave accents is an identifier. Okay, for resilience with pretty overloaded by that stuff. But okay, let's look at the create statement. There's one more thing. Syntax is described by SQL language. Syntax is described by the syntax diagram. Oh, this is nice. Let's go look at the create statement. Create data statement. There it is. So, what are the things that stand out, right? I need to be able to figure out. All right, you know what? Even the lexer, guys. I'm just gonna write the lexer for the create table statement. Like, there's so many keywords. There's so many freaking keywords. I'm gonna go crazy if I start writing them all out. But yeah, if I can write for the create table statement, it's just the amount of hours I need to put it to be able to write it for other stuff. But why can I not select everything? There we go. So let's copy. Also, let me check my phone real quick. One, two, three, four. All right. Let's focus over here. All right. So the lexer. Honestly, guys, I think the lexer should be its own in separate files. Sometimes I get overwhelmed by like how big these code files get. So I feel like there's two kinds of people. One who think like a bigger code file is okay because like they prefer that, and then there's people like me, you know, who prefer to have like smaller code chunks that are more logically organized. I think a part of this is because I used to code I code so much of my daily job stuff in C#, and in an object-oriented language like C#, the common convention is each class gets its own file, and very rarely do you have classes that like exceeding 2,000 lines of code. Although I've seen like in 11,000 lines of code, and some of my coworkers know which file I'm talking about when I say like 11,000 lines of code. I have this one coworker, Daniel. Him and I always get a good laugh when we run that one single test file. It's very common for people to not split their test files up and have these like ginormous files with all the unit tests. But anyway, I'm digressing again. So let's think of the keywords over here, right? We have a create, temp, temporary, table, if not exist, schema name. Okay. This is not a keyword. It's non-terminal. Yes, it's a grouping we need to understand the production for. Okay, so that's schema name. Same thing with, you know what? So there's a few of these. We shift Y. Okay, we have that guy. Who else? Oh, another one. Another one. Oh my god. We will keep making progress. We are not gonna give up with this stuff. It's the final countdown. So usually when I get tired, I switch Alexa on and I play Bezos once. So I'm just gonna do exactly that. Alexa, please play Bezos. Well, actually, no, do not play anything, Alexa. Stop. I will probably get a copyright because I want to put this stuff on YouTube and I'm playing a song. I don't know how that works. I'm not very smart with this stuff. But anyway, so we have these guys. So schema name, table name, column def, and table option. Let's go demystify those, right? Schema name, table name. Who could get me that? Like, what constitutes a schema name? I don't know. Let's go see. Keywords, aggregate functions, comments. I'm not supporting comments. Fuck that. I'm not parsing anything with comments right now. Expression. I think this is where we have schema. Well, no. Operators in parse affecting attributes, literal values. Okay. I bet you I could just do interesting schema name. Okay. So what else did we need? We needed schema name. Yeah, let's go figure out what a schema name is made out of. So schema name is, well, expression is that. Where else do you have a schema name out here? Where do you define schema name? No, man. I need to know what makes a schema name. Schema name has got to have something. Um, table column names. Create table left operand. Okay. Math functions on conflict. Window function with. Those are keywords. Actually, you know what? We already did keywords. Let's see. Is there aggregate functions, score functions, date and time functions, math functions with clause, reindex on conflict, save point with clause. I wish I could just click into this and go where I need to. SQL statement list, SQL statement, references. Okay, where's the create statement? Create view, create trigger, create table statement. Select statement, schema name. Jeez, it's pointing to everything but schema name. Why? Select name, table constraint, table options, column def. Okay, we have some references. Okay. The new table, if a schema name is specified, must either be main, temp, or the name of an attached database. Name. The table names that begin are reserved. Okay, so we do not care about that when parsing. Okay, these are the create table, statement creates public database, expression, column definitions, the default clause. Like, where do I find like what is a valid schema name? Then the new table is created to specify both a schema name and temp or temporary keyword. Oh, okay, so schema name could be, oh, okay, what's an attached database name? Hmm. Another database file to the current database connection. String the name database. Create table. Alright. Let's go look at a create. So I have a little program here called span rows. It's a Python program that just creates my that I need. Create table if not exists. Table name. Columns. The connection already exists, so I don't know why I need to attach anything. The name of an attached database. That doesn't sound right. Like, why does it create always? Okay. Create table specifies of the new table, the name of the new table, the date time in which the new table is created, the name of each column in the table, the declared type, the default value of expression for each column, option environment default table, both single and composite, user supported, a set of SQL constraints. I swear to God, I know I could use regular expressions to do this parsing, but because I want to grow the code I'm writing in the future, I'm choosing to spend time in learning this part as well. I want to like professionally work in just building like storage engines and stuff, and even going lower in the like abstraction layer in computer science, which is why I'm just not using regular expressions right now. But yes, if you were thinking just use regular expressions, I thought of that. I'm not doing it on purpose. Okay, I'm making my life harder. It's artificial complexities being added. Specify name. Okay. If not exists, create default clause, delete primary key. Constraints, row ID, response to constraint violations, column definition, select statement, table constraint, table options. I need something better, guys. Come on, something's gotta work for me over here. Overview and documents, technical and design document, SQLITE file format, debugging hints. Let's go back. SQLITE. Syntax, lang, HTML. It's gotta be in keywords, guys. It's gotta be in, no, not in keywords. It's gotta be an expression. Schema name dot table name dot column name. Okay. What about table name? Because that's actually something that I need in here, right? Literal values. Maybe integers, strings, blobs, or nulls. The syntax for okay has a decimal point or an exponential clause. It is less than. It's floating. Otherwise, it's a literal. The e character begins exponentiation. C language notation. Okay. A variable parameter token specifies a placeholder. The like, glob, regex, extract operators, the between operator, case expression. Okay, I think parse affecting sequence operators listed in precedence order, top to bottom, max to lowest. Expression. Okay. Not completely sure if I get this. Binary left associative, honest unary. Operator. Goddamn. Literal value represents a constant, maybe integers, floating point, numerical, literal. Okay, I'm gonna copy paste all this stuff because I need this. This is like a literal value would definitely be a token in here. So let's keep that. Schema name would be a production, and that would what we're looking for is schema name. Select statement. I don't know where select statement came. But so I'm just gonna keep the okay, so I have these guys as tokens, then literals. literals are something that I'll have to literals parameters. Okay, so these are also, so these would be keywords as well, like between. Okay, let's go back to this diagram for create. So create has these keywords. Schema name has some would be composed of literals. Table name would be composed of literals. And select statement. I don't know if that makes as much sense to me. Why the fuck would there be a select statement over there? References select statement. Let's just look at select statement. Oh my god, this is disgusting. So select distinct result. Okay, cool. Here's what we're gonna do. We're gonna behave that our creates do not use as. I literally like get a package when I look at how much code I need to write and how much code I've signed up for. Cool. Okay. So these are the keywords our Lexer needs to be able to chunk incoming streams into, right? So let's see. Current token, option string. Okay. At each point, well, this is a character position, right? So in a string character position, current token or last completed token. Let's just say that, right? Let's see current token, and every time you call next, you only ever get current token, next token, option string. Awesome. Okay, let's start with this. So character position, and I'm gonna put my dragon book away for a second, guys, so I can sort of make sense of this stuff. Character position, current token is initially none, next token is also initially none, right? And then you call different methods on it. Let's start with the peak next token, right? So peak next token, if map, okay, maybe I can use self dot next token dot if there is a next token that we have already parsed or read in memory, return that. So it's sort of like lazy loading, return that. Else read from input, store it, and return it. Okay. Yay, that makes sense to me. Very nice. Borat. I should stop with the Borat references. Oh, I've already coded like 2 hours since this morning, and there's a lot of freaking effort that this takes. I won't lie. I'm gonna go for like the next 20 minutes after a quick break, actually. So let me put you guys on pause, and I'll be back in a second to continue doing this.